for your patience in scheduling it. So I must say, to set the ground, that I feel a little bit scared giving this talk, because at least part of this material I don't feel very comfortable with, but it's still something I wanted to share with you, and so I'll give it a try. So I guess I like stories, and I like stories also in mathematics. And given all the recent progress in probabilistic understanding of conformal field theories, I thought, maybe I should also try to understand what it is about. And then I stumbled across this graph. This graph that should present a family of conformal field theories with central charge equal to 1. Okay, and they should all be related to the Gaussian free field. And of course, for me, Gaussian free field, I like it very much. And then I thought, maybe there is a story here. And of course, there is a story. There is a story in the physics literature, in this paper from the late 80s. There are newer physics stories, other conformal field theories with C equal to 1 that seem not to be on this graph. But these are not maybe stories that I can fully understand or appreciate. It seems that the language is different, and maybe you read it and you feel that there should be some other characters involved. So what the story I would like to find or discuss also today is a more probabilistic story. And why should there be such a probabilistic story? First, because these two axes of conformal field theories are related to the two-dimensional continuum free field. So this is very well known in the physics literature. Then one of these axes of C equals to 1 conformal field theories, the vertical axis, should all be related to this Ashkin-Teller model, which is a spin model that I will talk about, and which is gaining also interest again. And finally, if you see a continuously varying family of theories in the GFF, then for me at least two things come to mind, which are also related. One is some kind of chaos measures where you always have a continuum parameter. And the second is some geometric objects like the two-valued sets, which also have this continuously varying character. Okay, and it comes out that this imaginary chaos and two-valued sets, both of them are related to each other, and also related to the Ashkin-Teller model. So this all, it make me wonder whether there could be a nice story involving them all, maybe not a novel, but a short story of some kind. So I'm not going to tell you this story. I don't have it. There are some, small lines there. I'm not happy with all the translations. It seems to lack still depth for me. Something which really, gives color. The characters are at the moment having a small talk, but not so many insightful conversations yet. But still, I would like to talk about it. And today, maybe I like to introduce the characters and put front some very naive questions, and then towards the end come maybe to some rather concrete observations that might or might not lead somewhere. Okay, so we'll start with for me the local forks, the objects I do feel comfortable with, and of course the first the premier object is to do the continuum free field that I suppose all of you know well, and I'm pretty happy that now one can actually introduce it by just saying that this is the natural Schwarz distribution in 2 dimensions, satisfying the appropriate domain Markov property. Well, I mean, if I would say that, I guess I would be lying a little bit. We at the moment have some moment conditions, but I think at some point, sooner or later, one can just state it like this, introduce it like one introduces SLE, that this is the field with stationary independent increments and the only field with this property. But okay, let's also, for the sake of completeness, put down the usual definition we put for the free field, that this is some Gaussian process on the domain. You cannot define at points because the covariance kernel is too rough, but which you can index by some family of averaging functions. You can use some smooth functions or circle averages, and they'll get a well-defined process and even an analytic object with some continuity. So this basic object gives rise to many other objects, and I mean, here there are many people who have made wonderful progress on the multiplicative chaos, and in this talk, the relevant version will be imaginary multiplicative chaos. So this also goes back already almost 30 years to some random polymer literature. And for us, you know, it really is the exponential of I times the GFF. In general, you can define it for log correlated fields in any dimensions, but here we will fixate us from the beginning to N2 and the field just being the Gaussian free field. So if you wish, with 0 boundary conditions, but we will also look at it maybe on the sphere later. Okay, and how do you actually mathematically define it? You have to go through a regularization process, which is, I guess, quite standard by now. You take your favorite pointwise defined regularization. For example, here I've taken a circle average process, and then you take the exponential I beta of this thing, which is well defined, and then you normalize it. So in the case of real chaos, you take positive exponentials. This puts mass somehow on extreme values. You have to bring it the field down to get a non-trivial limit. Here, the field actually takes values on the circle, right? It's on the unit circle. It is kind of decorrelated. So in order to see anything non-trivial, you have to actually push it up. Okay, so you put this epsilon minus b squared over 2, and there is a limit how far you can go. You can basically go until the L2 boundary, until you can calculate second moments, and after that somehow things trivialize. There is too much decorrelation, so the only way to normalize it makes it become white noise. Okay, so here are 2 pictures by Janne of this with different parameters, and you see that it really there is more structure. You can see some structure on this beta 1 over square root of 2, but already later it's harder to see. Okay, but on the first one you really see a kind of nice structure appearing. So maybe some properties still of this field, and in comparison to this real chaos. So the real chaos really exists as a measure, okay, as an analytic object. The limit is in the space of measures. Well, the imaginary chaos, you can show that it really cannot be even a complex measure. It's merely a random distribution. And you can also see that it only really exists in the L2 phase. There is no similar argument to go beyond it as in the real chaos. You can look at the tails for T large. You see that real chaos has, we know that has polynomial tails. Imaginary chaos has actually very good tails, right? They are better than Gaussian tails. And indeed, all moments exist for imaginary chaos and can be used to determine its law, for example. So it's in nature a very different object, much more noise-like. For on the other hand, for the tails near zero, well, positive chaos is very difficult to make zero. You see it's super exponential. Well, negative chaos, imaginary chaos, it's much more noise-like, and actually, you know, it has a density everywhere, positive, smooth density, and you can see that the negative moments only or exist up to order 2. Okay, so there are some density results, etc. I would maybe also mention that there is this fun thing that these exponents in the moments seem to correspond nicely, like you know, the large tail exponents for imaginary chaos, small tail exponents for real chaos. It's Vincent Vargas who made me notice it. I think probably there is some nice explanation for it, but hasn't appeared in literature yet. But going on, well, one thing we know from real chaos is its multifractality. One way of looking at it is that it gives rise to this KPC relation. Well, imaginary chaos is monofractal. You don't see anything like thick points. It's really much more like a noise field. You will see rather things similar to fast points of the Brownian motion or so. Okay, and finally, there is something which is similar. There is a measurability of the underlying field with respect to this exponential, and in the imaginary case, it's actually maybe a little bit more surprising because it's something that wouldn't hold in the case of cascades. So here we use some continuity of the underlying field to actually see it. Okay, so this is one object. It's from maybe the main point from this slide is that it's still relatively well understood and something which probabilists feel comfortable working with. Another object is this two-valued local set of the free field. And this, you know, you think of as the analog of the exit time for the usual Brownian motion. So I take my Brownian motion, A and B. Here I've taken on this graph to be 1 and 1, and I look at the first time Brownian motion exits the interval, and I look at this interval as a random geometric set. Okay, so when I want to do the same thing for the 2D free field, the set would correspond to all points that can be reached from the boundary without the values of the GFF leaving this interval minus AB. So when I am with zero boundary conditions, this of course doesn't make directly sense because you don't have pointwise values on the GFF. But if you think even in the 1D case, you can give a different definition to these sets, a characterization using geometric and probabilistic properties as actually the smallest random set that induces the Markov decomposition of phi with constant boundary conditions, either equal to minus A or B. Okay, so this would also hold for this exit time for Brownian motion. If I look at the smallest time, stopping time, so that the boundary value is 1 or minus 1, it would be this exit time. Okay, and with Avelio and Wendelin, we showed that these sets really exist in the free field. There is a new phenomenon which was already noticed by, of course, Schramm and Sheffield of a certain gap that appears. They saw a height gap. Here we see that these two-valued sets can be only defined when there is a certain gap. But then you really get actually a two-parameter family of unique sets, as in the case of Brownian motion. And then you can study its properties. You can see that there are some sets with particular properties. The cascade dimension is something that will change. The loop dimension will always be locally SLE4. So it's something we still, you know, can work with and understand. So here are two examples. One is the first example. The simplest is A minus lambda lambda, which I've in this talk normalized the GFF so that lambda is equal to pi over 2. And then is the other example we like to get this. So this is one of the smallest ones where each two loops, they were actually, the boundaries are really just curves. And over the curves, the boundary values always change. And the other maybe special case is the CLE4, where the labels or the boundary values inside each loop are really independent. And in fact, this is the only case where they are all independent, interestingly. Okay, so let me try to tell you now that these two objects are intimately connected. And this was really noticed by Avelio, Lucas, and Frederick, where they when they proved the Hausdorff dimension result of these two-valued sets. And moreover, they showed something very interesting. They showed that you can construct a certain conformal Minkowski content on these sets by restricting the real part of imaginary chaos with a special parameter. Okay, and so it's not shown that this is exactly the Minkowski content of the set, I think, but it's something similar. You should think of it in a similar way. So the expected Minkowski dimension of these sets was known. This is an argument by Schramm, Sheffield, and Wilson that we used in our paper with Avelio and Wendelin already, which uses which relates these dimensions to Brownian motion exit times actually, and then certain expected dimension you can easily calculate. So the highlight of this paper for me was really making this connection to imaginary chaos to get almost your Hausdorff dimension. And let me try to give you maybe just one or even two ways to see that there is some connection between these objects. Okay, so the first observation goes as following. I will denote the set by just A. Okay, and then I can, for every point, I can look at the conformal radius of this of the complement of this casket seen from the point set. Okay, so that set is some fixed point, and then you can calculate. Okay, so if I go to point 0, then the expectation of the imaginary chaos at this point, which you can make sense of by normalization, is just equal to 1. I can calculate this expectation by taking conditional expectation with respect to my two-valued sets. Okay, and what then comes out is one extra independent GFF that if I take the expectation will give me the conformal radius, and then there will be the boundary value. Okay, and the boundary value will be either A or minus A. Okay, and with equal probability by symmetry. And this will give you this cosine term because it's exponential I beta A plus exponential minus I beta A. Okay. And now if you look at this expression, you observe that the conformal radius of minus beta squared over 2 blows up, exactly at a certain value when when you take A equal to pi over 2 beta. Okay, for a smaller A, it's nicely finite, and then it blows up. Okay, and this if you have recently had to give a course on Brownian motion, you of course you realize that this is related to the exit time of Brownian motion from the interval. Okay, so I'm using imaginary chaos to understand the law of this conformal radius of the loop ensemble. And I see that there is this special relation which appeared also in their theorem. Okay, and there is another way to actually think about this. is that the circle average. Now I look at another Brownian motion in the GFF, which is the circle average process. It's a time-changed Brownian motion. So this is an observation Guillaume Bavarez told me about. And then in the real chaos, you reweight things by exponential of gamma GFF, and you add a drift or Brownian motion. But you can reweight things by the cosine of beta of the GFF, which would be the real part of the imaginary chaos. And if you reweight this Brownian motion by this, you are actually constraining the Brownian motion to stay in a certain interval. And this interval is really actually this beta minus 2 beta pi over 2 beta, minus pi over 2 beta, pi over 2 beta. And again, you can make the connection that if a point is on the two-valued set, shouldn't the circle average kind of be in this interval, because the boundary values are a and minus a, and maybe if I take the average, it should be always smaller than that. Okay, of course, there is actually an extra fluctuation, so it's not so immediate. But it's a nice observation that you also get some sort of atypical points which have a non-trivial dimension by restricting them to stay long-term in an interval, not having a drift. Okay, so this is, we have imaginary chaos, we have two-valued sets, they are related. Let's talk a little bit about the third character which comes up in the probability literature. Okay, so this is, really I'm presenting you characters maybe a little bit too much like they do in this police investigation, but I hope they are friendlier. They are not criminals. They are friendly people. Okay, so Ashkin-Teller model. So this is a certain lattice spin models where we start from. I don't know why I put independent here. We start from two Ising models, and we can start from two independent Ising models, and then we couple them together. Okay, so the Hamiltonian really is two independent Isings, which is this first part. They both have the same temperature, and then I've added some coupling for the 4 spins. Okay, so if K4 is equal to 0, I have just 2 copies of the Ising model, and otherwise there is some coupling, putting them together. And I see there is this minus actually counts for all the things. Both of these constants are positive. So it comes out in this spin model, and this is known in the physics literature. There is a whole line of second-order phase transitions. Okay, so whole one-parameter family of second-order phase transitions, which then, in the continuum limit should give rise to conformal field theories. And on this line, there are some special points. There is the XOR Ising, which is really 2 independent Ising models put together. There is the 4 pots model. And then there is some integrable point by Fadeev Samologikov, which has quite a complicated K value, and that I really don't know much else to say about other than that it looks interesting and fascinating. So there is lots of physics work about this Ashkin-Teller model from long ago. It is known to have connections to the 6-vertex, 8-vertex models, to compactified free field. There have been calculations of correlation functions on domains, on spheres, on the torus, and even higher genus Riemann surfaces. There's also some contemporary work on that that goes to computational analytic studies of interfaces, of trying to understand even better in more detail the conformal field theory of the scaling limit, calculation of more correlation functions. So some were calculated, but not all in the physics, in the older physics literature. So there are some very, very recent papers trying to do all of it. And there is also recent mathematical work on it by Dumesnil-Copin, Sacha, Marcin, Wey, etc., where they have introduced new representations and combinatorics of this model. In special points, looked at the continuum limits, considered links to height functions, etc. Okay, and then there is a very particular work at a special point, which is the convergence of the spin field that I will tell about just in a moment. Okay. So now I will try to tell you about the connections of this Ashkin-Teller model and the imaginary chaos and two-valued sets, and then we have connected them mathematical objects. So the theorem by Janne, Eero, and Christian is that if you look at the renormalized spin field, so this is the product of two spins of the XOR Ising model. So this was the Ising spins were independent. Then this converges to the real part of imaginary chaos for the 2D GFF with a certain parameter beta. Okay. So the proof actually is based on moment calculations. So the endpoint correlation functions for the Ising model are known. This is some very deep work by Chelkak, Hongler, Isurov, and probably others too. And as I said, in the case of imaginary chaos, you can calculate the moments, and especially in the case where your covariance kernel is well known. These are explicit things that were calculated in this paper, and basically to prove the convergence, you just show that the moments converge. Okay. And what is the relation of this XOR Ising, which a specific point of Ashkin-Teller and two-valued sets? Well, there is a recent theorem also by Dumesnil-Copin, Lys, and Qian that, well, it in the beginning when I stated it's not so clear what is the relation to this Ashkin-Teller model or XOR Ising, because actually to prove a scaling limit, they have to look at the related combinatorial structure, the double random current. And they show that the boundaries of those, outer boundary, the inner boundaries in different boundary conditions converge to different two-valued sets. Okay, so we see the usual CLE4 appearing, the A minus 2 lambda 2 lambda, but also something a little bit more interesting, minus A minus square root of 2 lambda, square root of 2 lambda. And in fact, they had also a conjecture on the XOR Ising interfaces. With certain boundary conditions where you would see even something different. So A minus square root of 2 plus 1 lambda and symmetrically. Okay, and just as a remark, you know, this minus square root of 2, if you combine it together with this 1 over square root of 2 is exactly what we saw before in the relation between imaginary chaos and two-valued sets. Okay, so the scaling limits seem to come up with a similar relation. And in fact, there are convergence conjectures for the Ashkin-Teller model for the whole critical line. You should see the cosine beta appearing for the GFF, and you should see the two-valued sets A minus AA appearing. So from the physics literature, you know, you can come up. They do have because, as I said already, there they understood the relation between kind of compactified GFF with values in a circle and this Ashkin-Teller model. So you can come up with some correspondence between this beta and the coupling constant, which doesn't read so simply. And Marcin has also a very nice explicit conjecture on the interfaces. Okay, and in fact, this conjecture also comes in two parts. One on this boundaries of double random current, and then also on the spin field. And you know, he told me that he hasn't publicly announced it, so I thought that I will leave him this pleasure, even if he told me that I can say it, and I will limit myself to saying that this relation between imaginary chaos and two-valued sets that we saw in the continuum appearing to through some dimension arguments does appear in these conjectures too. Okay, so these are the players, probability community, I guess, feels comfortable working with, at least to some degree. It's not that we understand everything. It's not that we can prove everything we would like. Certainly not. There are these scaling limit conjectures, I think, very exciting, and then probably not easy at all. But okay, these are objects you feel comfortable with. And now I would like to introduce in the room this foreign gentleman of standing, who I have to admit I don't understand too well. Maybe the accent, he's speaking a little bit with an accent, but let me try to talk about it, her a little bit. Okay, so this is conformal field theory, and you can think of conformal field theory in many ways. I think there are many ways of trying to also make it afterwards rigorous, but also for thinking, you can first think of it as some abstract collection of objects, which are your fields or operators. They are defined kind of, they take values for each point in your, say, on the Riemann sphere or on your Riemann surface. They do take a value. Let's work on the Riemann sphere. So then you do ask that they behave in a certain way for scaling. Well, this is some collection. What kind of objects, maybe it's not so important. You just say that, okay, I have certain operation on these objects, which you call a correlation function. So this is some multilinear map, and these values you really want to be, in complex numbers. So this is something which will encode information. And then you ask that, okay, there is some sort of product on these fields or operators. You can, if you bring the points close together, then you give rise to another field or operator that you can actually expand. So this is, you say that your fields are also, the collection of fields is rich enough so that you can always expand these products again as a sum of fields. And then here the coefficients are certain functions, the functions that depend actually on the distance between the points, and then some numerical information. And every time you write an equality, you say, okay, it just has to hold inside these correlation functions, and then you don't need to really think about the nature of your fields or operators. You want to encode, at the moment, it's just a field theory that I told you. You want to encode conformal symmetry somehow. And so what you do is you say that actually there is some symmetry operator that acts on all of this data, and a convenient way to encode it is actually introducing another operator or a field in your theory that has a certain expansion that actually encodes. It's like kind of written as a series of all of the basis of the conformal symmetry group. Okay, so we have this is basically the data we have. So we have some fields or operators with some scaling components. We have some way of talking about their correlations. We have then an operation, this product that gives you some expansions, and then symmetry. Okay, and if you think just very abstractly with it, you already have many vague questions. So you saw what were kind of the data that we were giving here. Were fields, okay, but maybe their nature is unclear, but definitely these dimensions. Definitely there was a real number C here, which is the central charge, and there were these functions here. These were also really, functions. And so you can ask that if I'm giving such a data, does a conformal field theory exist? Okay, and what does it mean to exist? It means that everything I've told you is consistent. I told you that something has to be, some product has to be commutative, it has to be associative, etc. And these give you consistency conditions. And these conditions are actually not easy to check. So if one is given just the central charge, these kind of structure constant, 3-point constants, and the dimensions, it's not easy to say whether a CFT with this data exists or not. Okay, and if you manage to at least give some examples, you might ask what are all the examples of CFTs I can have, and this is of course a very difficult question, but you know, there are partial classifications. Say you know, if you start classifying first, there is this real parameter C. You can classify them based on that, but they only offer a partial classification because there can be many conformal field theories with the same central charge. So then you can go and ask, you know, can I classify all conformal field theories with a given central charge? And this already becomes an interesting question. Or okay, you know, another question is, can you calculate all correlation functions given a certain data? But this is, of course, all very vague, and you know, at least I feel as a mathematician a bit uncomfortable, even if these questions seem exciting to me, and you would like to find the context where it's you're sure that you know what you're doing. And you can realize conformal field theories or start working with them in the realm of probability. So, I mean, for many of you, this is clear, of course, but let me still go through it. And here I follow this. There is this nice unpublished book, which I hope one day will be published by Franck Gabriel, Clément Hongler, and Francesco Spadaro. And they really give this lattice and then probabilistic view on CFT. And you know, you don't have to do much. You first say that, okay, I will put all the information on a common probability space, and in particular, I try to encode these fields also on this probability space just as random functions. Okay. And then, well, it comes out that these random functions really are too rough to exist in many cases. These fields or operators, you cannot really. I believe there are probably you know, theorems saying that you cannot realize them as random distributions. So you only say that, okay, let me just try to approximate them and say that I want to have convergence in as epsilon goes to 0. Okay, so for a concrete example, if you take just this exponential of the GFF, and you take exponential of million times GFF, then you know that you cannot make sense of this limit. Okay, but if you take 2 points, then you can make sense of the correlation function by just approximating by epsilon, and this 2-point correlation function will just converge for all values of your exponent. There is no problem. Even if the field doesn't converge in any natural sense, the correlation functions by approximation might very well converge. Okay, and in the nice cases, you might actually be able to choose these fields to be holomorphic, or as I said, in some cases, if the, for example, exponent for the in the exponential of the GFF is small, you can get the limit as an analytic object, and then as a probabilist, you're even happier. Okay, but you might want to have rougher fields, and you might want to even allow fields that are not single-valued and become single-valued only in correlation functions. Okay, so this, but on the level of epsilon, you can well define all of these things. And you might say that we realize a certain conformal field theory in a probabilistic framework when you get the same basic data, the same dimensions, the same kind of this 3-point constants, the same central charge. And you know, if you actually have a path integral, then things are even nicer, because some consistency conditions for correlation functions come almost by definition, because there is a unique way to define a 4-point correlation function. Okay, so this is at least some framework in which we can talk. So we have these random fields for which at least we can talk about correlation functions. And let's now look at this C equals to 1, the conformal field theories with this parameter that should correspond to the GFF. Okay, in the physics literature, you will find many of them. So first of all are really free field based. So one is this x-axis here. So this should correspond to compactified free field. So as a mathematician, we will come back to it, but compactified free field should be, you can think of it that I just look at the map to the circle and not to the reals, and I use the same Dirichlet energy as for the reals, okay? So this is how you can think. Then there is a certain thing called orbifold GFF. This is the one that should correspond to the Ashkin-Teller model on the y-axis. Here, you don't look at the values in S1, but you actually mod it out by Z2. You say that things under reflection are the same, and these conformal field theories are the one that should be related to the Ashkin-Teller model. Okay, and then you start finding that in the newer literature there are more. There is everyone or many are looking at this Liouville conformal field theory. There's a parameter Q there, which a priori is a real parameter bigger or equal to 2 and gives you conformal theories, field theories with C, I don't know, bigger than 25 or something like that. But if you put Q, just make it 0, you will also get C equals to 1 conformal field theory, and there are actually, correlation functions or 3-point constants conjecture for that as well. And there is recent very nice progress on that by Morris and Shin. And then there is another theory called Runkel-Watts theory, which is came someone in 2001 as some certain limit of theories that are C less than 1. So these are the theories that usually correspond to the kind of lattice models like the Ising model, etc. And I put here the question marks because I'm actually not sure whether it has been shown that you can define these theories on all Riemann surfaces and all consistency conditions hold. Okay, so this would be showing that really a conformal field theory exists. And as far as I know, there are some recent work on this, both Runkel-Watts and Liouville in the physics literature, showing that at least 4-point things on the sphere are well defined. But maybe I'm wrong, but I think it's not fully known. Okay, and recently there was some conformal field theory based on the Brownian loop sup that you can also where you can also twine the parameter C to be equal to 1. Okay, and the naive questions you can ask just by this is this list exhaustive? Okay, so in the physics literature, they actually at some point thought that this already this blacklist is exhaustive, at least when you also ask that things are consistent on the torus, and at least you expect that everything you can get from the GFF should be there. And you can ask some other questions which are maybe not important, but already from the physics perspective, it's not fully solved. But as said, physics is difficult. Probability is simpler. So let's see some naive, questions that the probabilistic object would ask from their friend conformal field theory, and this would be, can you give a probabilistic construction of this space of conformal field theories? That would be your basic condition, and there is a construction by Kang and Makarov of the CFT of the usual GFF. So that would be you can think of as a limit when you send this compactified GFF radius to infinity. You make your circle larger and larger. So there is a whole long article treating this and the relation to SLE. And basically, the x-axis, the part of compactified GFF CFT, you can set up in the similar way. And well, there are some questions there. Many fields are very rough. So as I said, for example, you make K very large. There's no hope of making sense of this field as a random distribution. Or if you take, the derivative of the GFF and the product of it, it's something that just doesn't exist because the derivative is already of the regularity of white noise, and taking a product of white noise with itself is a kind of all those who have tried, they probably agree with me. It's quite an impossible task. You will always end up with some other type of white noise. But if you take the point of view that I just work with correlation functions, I just regularize, I check that then these correlation functions have a limit. There is no big problem. If you go to physics literature, you see that actually they will look at something to make the theory complete, to get kind of all the whole set of operators. They will look at something called the holomorphic GFF. Okay, so something you would like to say is you imagine that the GFF is harmonic, then you take the conjugate harmonic function, and puff, you get something holomorphic. Okay, and in correlation functions that happens. If you take GFF correlation functions, they are harmonic. You can take then the conjugate harmonic function, and you just get the complex log. But of course, probabilistically, GFF is not a harmonic function. Taking a conjugate harmonic thing doesn't make sense just like that. But again, if you go to the level of approximations, there are many ways, because a priori, if you, for example, just project it on things that are linear inside triangles in the triangulation, you can define harmonic conjugates along paths. Okay, so if you go along a vertex, then the value might change, but as long as you don't do that, it's nicely single valued. Okay, you might already lose nights over what is a compactified GFF, because you can mathematically you can find at least 3 definitions, and it's not clear whether they all agree with what you see in the physics literature. But still, you can set it all up. One question which I think still remains is that you see there are special points on this graph. There is first of all, there is this nice, already there is a nice flow on the set of conformal filters, and then there are points with extra symmetries. And these extra symmetries are something that go a little bit out from the framework of, at least it's not discussed in Kang-Makarov. This is something you might be interested in looking at. And also, if you go to the orbifold line, you certainly need a little bit more. There are something called the twist fields, and which are a little bit mysterious in the physics literature. But my feeling is that today Titus arrived in Lausanne. He told me a beautiful story that he has come up with, and I think he maybe has solved this part of the question. Maybe there is a way to construct these twist fields. Maybe I'm too optimistic, but I have a feeling that there might be something. Okay, so this is some probabilistic, naive probabilistic questions. You can ask also similar things in the random geometry. I try to speed up now because I want to come to some more concrete observations as well. But in random geometry, I mean, I personally, what I would very much like to see is to give an interpretation of this graph using, for example, different two-valued sets. Finding geometric observables representing these operators, like, for example, this conformal radius to some power that appears both in imaginary chaos and recent work of Morris and Chin. For these twist fields, understand whether there are some geometric symmetries at special points, etc., etc. Okay. So that would be something. I don't know if there is something, but that would be close to my heart. And just to say that there is, in addition to these probabilistic stories, of course, or maybe not of course, maybe rather interestingly, also new papers on the C equals to 1 CFTs in the physics literature, and they maybe look at more complicated things. They go for 4-point correlation functions. These 4-point correlation functions have interesting expansions depending on how you write them. You can take operator products of first two fields and other two fields, and then kind of write what you get and use some orthogonality and get the expansion here, or you could do something different. And in these expansions, you have these interesting objects which are called conformal blocks. So you have this kind of functions or constants we were looking at. Then you have conformal blocks which should not depend on the model. So this should be really functions that depend only on this point t on the sphere, the central charge, and the dimensions. Okay, and then otherwise really universal. But it comes out that these functions are not easy to write down. They have difficult expansions. So understanding those in this simple case c equals to 1 has seen new interest. And in particular, there has been kind of a nice new wave making connections between these conformal blocks and certain things called tau functions that seem to be that especially come from this works by this ancient French prime minister. And it comes out that these tau functions somehow they help to represent these conformal blocks and are easier to work with. And secondly, also actually, it comes out that these conformal blocks are still not fully understood even in the c equals to 1 case. There has been the study of what are called degenerate conformal blocks. Okay, and so there are some interesting works that, of course, I have not almost any understanding of, but I would like to have. Okay, so this is almost all. I would just like to finish with some what I would call anecdotes. So that was a small talk. Anecdotes, you might or might not find them funny, but they are at least usually there is something precise there. And these are some smaller observations. So in fact, it's not the first time that if I see some interesting object and I ask, has someone in probability literature worked on it, I see that Juhan Aru has already worked on it and has done something interesting. So these tau functions that came up on the last slide and are related to 4-point correlation functions in c equals to 1 conformal field theories. This come up in work of Juhan, and when he was studying the convergence of timers and the interfaces, and he found a nice expression for this tau functions in upper half plane using CLE 4, and here rho is some representation of the actually the fundamental group on the punctured sphere, and the representation has a certain we put some conditions on it. We want it to be unipotent so that just individual loops wouldn't count. So then the trace is equal to 2, and if just one loop, if a loop just surrounds one point, it gives no contribution. So it's somehow encoding the loop ensemble via these representations, and it comes out that there is enough information to encode actually the whole loop ensemble geometry there. If I look at this right-hand side geometric, CLE4 thing, it seems to me to be very similar. I'm probably too naive to this conformal radius operator again, which is in imaginary chaos, and the work of Morris and Shin. And you might say, okay, it's really not the same thing, because on one I'm looking at loops that surround several points. These are the non-trivial contributions. Here, the conformal radius, you look until you find a loop that surrounds just one point. But let me show you a elementary calculation. Okay, so you work on the upper half plane with n equals to 2, And you can calculate from the side of these tau functions. I set omega equal to this trace. So if it's surrounding 1 point, as I said, it will be just equal to 1. So I'm only looking at the loops, nested CLE4 loops that surround 2 points. So this is some random variable n. And the formula tells you that this tau function for 2 points in a simply connected domain is written like this. It's 2 to the minus n, and then this omega to the power n. And here is this random number of loops that surround these 2 points, this finite number. Okay, and I claim that you can calculate it also from the side of imaginary chaos. Well, I first I choose points to be of unit distance. This is I can do always by scaling, and I calculate again this expectation using conditional expectation with respect to the largest loop that kind of separate the 2 points. And when you do that, what you get is this formula here. Okay, is you have some omega tilde, which is some just some number that depends on the betas I have chosen. And I have this 2 to the minus n. I have some other cosine, and then I have the expectation, the two-point function of this conformal radius operators. Okay, and for me, it's a very elementary computation, but it aroused some of my interest, saying that, okay, is there some interesting story here? And let me maybe throw in a final calculation before ending, which is a calculation that relates also this Liouville CFT in the game, because there is a known connection between the GFF CFT and Liouville, which is that the 4 pots should be represented somehow by both of them or related to both of them. Okay, and so there is on this Liouville side, there is this very nice recent progress by Morris and Chin, where they take this 3-point function from the literature, they reinterpret it, they renormalize it, they find a nice geometric way to reinterpret it, and then they find some sort of 3-point formula. Okay. So this formula is very scary. It's really lots of terms, but if you put in C equals to 1, kappa equals to 4, it simplifies quite a bit. Okay, you get something like that. These lambda I are nicely some -1/2 squares, and you have just this epsilon function that might still be scary, but it's an explicit entire function with some integral representation related to double gamma functions. Okay, so you have this formula, and here, in fact, this CLE4 is up to the distances of the points. It's really again this operator on this conformal radius powers. Okay, and I claim that this cosine that appears here is again the same cosine that we saw just 2 slides before, and that we saw at the beginning of the talk. Okay, that this is related to this same conformal radius calculation. And again, the only thing I can do is a very naive computation. I set again 1 point to 0. I set the 2 other weights to minus beta squared a half. Then what you get from their formula is this formula, and actually you get exactly the same formula when you take conditional expectations in this imaginary chaos correlation, where if I work on the sphere, I want to put the weights to be opposite of each other, so that the additive constant of the GFF wouldn't matter. Okay, 2 points is maybe too simple. So what happens with 3 points? Can you go to higher points, 4 points? Well, I don't know. Maybe you can also throw in these tau functions from just before, the TVS. For me, this looks exciting, but it's also possible that these very trivial computations with 2 points, will will stop working later on. But in any case, I wanted to share. I thought that these were kind of anecdotes, which I hope you found funny. That's all I have to share. I would be happy to discuss now in the limits of my limited knowledge, of course. Thank you very much.